A single locomotive can pull a train weighing 10,000 tons, 10 million pounds, the equivalent of 140 fully loaded tractor trailers, connected in a line stretching over a mile, moving at 60 miles per hour across terrain that would stop a convoy of trucks cold. A semi-truck hauling maximum legal weight, 80,000 pounds, strains to climb a 6% grade. The engine roars, the transmission downshifts, speed drops to a crawl. That same grade for a freight locomotive pulling 10,000 tons is a minor inconvenience. Yet the engineer adjusts the throttle slightly. The train continues. The disparity isn't just impressive, it's fundamental to how modern economies move bulk goods, coal, grain, steel, containers, across continents. But the physics that make it possible aren't obvious. They're counterintuitive. And they depend on a principle that seems like it should work against the locomotive, not for it. This is the story of steel on steel, friction, and why the weakest link in the system is also its greatest strength. The problem starts with traction. A locomotive needs to push against something to move forward. Cars and trucks push against the road through rubber tires, soft, grippy surfaces that deform slightly to create friction. Locomotives push against steel rails through steel wheels. Hard on hard, smooth on smooth. By every intuitive measure, this should be terrible for traction. Steel wheels on steel rails have a coefficient of friction around 0.25, meaning the locomotive can only convert about 25% of its weight into forward pushing force before the wheels start slipping. Rubber on asphalt, by comparison, has a coefficient around 0.7 to 0.9. A truck with the same weight as a locomotive should have nearly 4 times the traction. It doesn't. Because the real question isn't how much traction you have, it's how much resistance you're fighting. A rolling resistance, the energy required to keep something moving, depends on how much the wheel and the surface deform under load. Rubber tires compress and flex with every rotation. That flexing absorbs energy. Steel wheels on steel rails barely deform at all. The contact patch, the tiny area where wheel meets rail, is measured in square inches, not square feet. The pressure is enormous, but the deformation is minimal. A steel wheel rolling on a steel rail has a rolling resistance coefficient around 0.001 to 0.002. A rubber on asphalt is 0.01 to 0.015, 10 times higher. That means moving a freight car on rails requires 1/10 the energy of moving the same weight on a highway. That's the trade. Locomotives sacrifice traction for efficiency. And because trains operate on fixed routes with controlled grades, the efficiency matters far more than the traction. But traction still matters. A 200-ton locomotive pulling a 10,000-ton train is working with a traction-to-weight ratio that leaves almost no margin for error. Add the slightest wheel slip, caused by oil on the rails, wet leaves, ice, or even overly aggressive throttle application, and the locomotive loses grip entirely. The wheels spin uselessly. The train stalls. Railroad engineers have been fighting this problem since the 1830s. Early solutions were crude. Sand dropped onto the rails ahead of the drive wheels to increase friction. It worked, but only temporarily. The sand was thrown clear after a few wheel rotations. Our locomotives carried sandboxes, refilled at every stop, to keep traction during climbs or in wet conditions. By the 1920s, steam locomotives were reaching the limits of what adhesion could support. A single locomotive, even a massive articulated design like the Union Pacific Big Boy, could only convert about 135,000 pounds of weight into tractive effort before the wheels slipped. To pull heavier trains, railroads added more locomotives, 2, 3, sometimes 4 engines on a single train. And it worked, but it was expensive. Each locomotive required a crew, fuel, and maintenance. The diesel-electric locomotive changed the equation, not because it had better traction, it didn't, but because it allowed precise control of wheel slip. A diesel-electric doesn't drive the wheels directly. The diesel engine turns a generator, which produces electricity. That electricity powers traction motors mounted on the axles. Each wheel is driven independently by its own motor. If one wheel starts to slip, If the electrical system can reduce power to that specific motor while maintaining power to the others, the engineer doesn't even need to intervene. The system corrects in milliseconds. This is called distributed traction control, and it allows a diesel-electric to operate much closer to the adhesion limit without catastrophic wheel slip. A steam locomotive, with all its drive wheels connected by rigid rods, couldn't do this. If one wheel slipped, they all slipped. The result was that diesel-electrics could haul heavier trains with fewer locomotives. A single modern freight locomotive, a 6-axle, 4,400 horsepower unit, can produce around 130,000 to 140,000 pounds of starting tractive effort. That's comparable to a big boy, but in a machine that weighs half as much and doesn't require a fireman shoveling coal. Modern freight trains routinely use multiple diesel-electrics in what's called a consist. 2, 3, or more locomotives coupled together, all controlled by a single engineer in the lead unit. The locomotives communicate electronically, coordinating their power output to avoid wheel slip and distribute the pulling force evenly across the train. A typical heavy freight consist might have 3 or 4 locomotives producing a combined 500,000 to 600,000 pounds of tractive effort. That's enough to move 15,000 tons on level track or 10,000 tons over moderate grades. But tractive effort isn't the only constraint. Now there's also drawbar pull, the actual force transmitted through the couplers connecting the cars. This is where trains start to behave less like a single rigid object and more like a chain of loosely connected masses. When a locomotive accelerates, it pulls the first car pulls the second pulls the third. Each connection absorbs some of the force through slack in the couplers, the small gaps that allow the cars to move slightly independently. In a 100-car train, there might be several feet of total slack distributed across all the couplings. If the engineer applies too much throttle too quickly, the slack runs out suddenly. The couplers slam together. The shock can break couplings, damage lading, or even derail cars. Skilled engineers manage this by applying power gently, taking up the slack gradually, and timing throttle increases to keep the train stretched. All couplers under tension, no sudden jerks. Descending a grade reverses the problem. Gravity pulls the rear of the train downhill faster than the front, compressing the slack. If the engineer applies too much braking force at the front, the rear cars can push forward, creating what's called a run-in. In extreme cases, the momentum of the rear cars can lift the wheels of the front cars off the rails, causing a stringline derailment. Managing these forces requires understanding the train as a dynamic system, not a static load. The distributed power systems used on modern heavy freights help with this. Locomotives placed mid-train or at the rear can apply pulling or braking force independently, reducing the stress on individual couplers and allowing smoother control over steep terrain. The grades themselves are another constraint. A fully loaded freight train can maintain speed on grades up to about 1%, a rise of 1 foot per 100 feet of horizontal distance. Steeper than that, and the train starts slowing unless additional locomotives are added. Grades above 2% require helper locomotives, extra engines added mid-train or pushing from the rear to maintain momentum. The steepest mainline railroad grades in the United States are around 3% to 4%. These sections, like the climb over the Appalachian Mountains or the grades in the Sierra Nevada, dictate how heavy trains can operate across entire rail networks. Railroads avoid steep grades whenever possible, sometimes building tunnels, bridges, or circuitous routes to reduce the gradient. The reason is energy. Lifting 10,000 tons up a 1% grade for 1 mile requires about 50 million foot-pounds of work. At 2%, it's 100 million. The locomotives have the power. Modern 6-axle units produce around 3.3 million foot-pounds of work per minute at full throttle. But sustaining that power output for hours at a time generates enormous heat in the traction motors, the diesel engine, and the cooling systems. Eventually, something overheats or breaks. Lighter trains can handle steeper grades. Passenger trains, with only a few hundred tons of total weight, can climb grades that would stop a freight train cold. the fastest passenger rail lines in the world. The Japanese Shinkansen, the French TGV, operate on routes with grades up to 4% because the trains are light enough and powerful enough to maintain speed. Freight trains don't have that luxury. They move bulk commodities, coal, grain, ore, petroleum, where the economics depend on moving as much weight as possible per trip. A unit train hauling coal from Wyoming to a power plant in the Midwest might consist of 120 cars, each loaded with 120 tons of coal. Total trailing weight, 14,400 tons. The locomotives pulling that train aren't just moving the coal, they're moving the steel of the cars themselves, another 3,000 to 4,000 tons. That's why railroads are so efficient for bulk freight. Yes, the energy required to move a ton of cargo by rail is about 1/3 of what's required by truck. On a ton-mile basis, the industry standard for measuring freight efficiency, trains use 0.2 to 0.3 gallons of fuel per 1,000 ton-miles. Trucks use 0.7 to 1.0 gallons. The difference compounds over long distances. A 2,000-mile haul by train consumes a fraction of the fuel a convoy of trucks would burn covering the same distance with the same cargo. The efficiency comes from steel on steel, the low rolling resistance, the ability to connect dozens of cars into a single train controlled by a small crew. The infrastructure, rails, signals, bridges, built to handle enormous concentrated loads moving at predictable speeds along fixed routes. But it all depends on that fragile point of contact. Steel wheel on steel rail. A contact patch the size of a dime, carrying hundreds of tons, transmitting hundreds of thousands of pounds of force without slipping, without deforming, without failing. Yet it's a system that works because it's on the edge of failure. The coefficient of friction is just high enough to provide traction. The rolling resistance is just low enough to allow movement. The locomotives are just powerful enough to overcome grades and accelerate the mass. The couplers are just strong enough to hold the train together. Push any of these variables too far and the system breaks. Too much throttle and the wheels slip. Too steep a grade and the train stalls. Too much slack action and couplers fail. Too much speed into a curve and centrifugal force lifts the wheels off the inside rail. Railroad engineering is about operating within these margins, designing routes that avoid steep grades, calculating tonnage limits for specific locomotives on specific terrain, training engineers to manage throttle and brakes to keep the train stretched and stable, installing distributed power systems to reduce coupler stress, building detection systems to warn of wheel slip, overheating, or bearing failure before catastrophic damage occurs. The result is a transportation system that can move absurd amounts of weight with relative efficiency and safety. A single crew operating a consist of locomotives can move more freight in one trip than 100 truck drivers hauling for a week. The energy consumption per ton-mile is lower. The labor cost is lower. The infrastructure cost, amortized over decades of use, is lower. It's not faster than trucks. It's not more flexible. But for moving bulk commodities across long distances, nothing else comes close. And it all comes down to steel on steel. The paradox of low traction and low resistance. The engineering that turns a weakness into an advantage. The careful balance of forces that allows a machine to pull 100 times its own weight across a continent without breaking apart. A locomotive can pull so much weight because the rails let it, because the wheels barely resist, because the system is designed to operate at the edge of what physics allows. That's the answer. Not power, not size, efficiency. The art of doing more with less friction.